Let's now try to design a Mealy FSM to detect the sequence 101. Overlapping sequences are not allowed. Before we start doing that, let's learn a few things about a Mealy machine. So in a Mealy machine, your output is a function of your current state and input. Remember, your more was where the output was a function only of the current state. So this is for a more. The second thing is, in a Mealy machine, the number of states is equals to the length of the sequence. So number of states is equals to sequence length. So if your sequence is 3 bits long, then your number of states will be at most 3. Remember that in a more machine, the number of states is equals to sequence length plus 1. So that's point number 2. Point number 3 is that in a Mealy machine, output is asserted in the same cycle when the sequence is detected. In the more machine, output lags by 1 clock cycle. So using this information, let's try to figure out the table here. Now we want to detect 101. Overlapping sequences are not allowed. So this is the first instance where 101 is detected. So your output will be asserted in clock cycle 5 itself. In the more machine, your output would have been asserted in cycle 6. The second instance where 101 is detected is this one here. So your output is asserted in cycle 12. Remember, overlapping sequences are not allowed. If the overlapping sequences were allowed, this would have been your second instance of your sequence, and your output would have been asserted in cycle 7. But since overlapping sequences are not allowed, we are going to ignore it. Now let's try to come up with the state diagram. Remember, we are trying to detect 101. So let's see the process. So this is your state S0, which you can attain by resetting the circuit. So S0 is your reset. Now from S0, if I get a 1, I move to state S1. So we go along with the path in which we can detect the sequence. Now in the Mealy machine, your output is written on the transition. So if you're in the state S0 and you get an input 1, so input is this one here, you move to state S1, but your output is still a 0. So we are going to write S1 as a state which can be reached from the reset state after you get an input 1. Now S1, or from S1, if you get 0, you move to the state S2 and you haven't still detected your sequence, so your output is a 0. So S2 is a state which you can reach from the reset state if you have the bit pattern 1 0. Now remember, here I've said that the number of states in the Mealy machine is equals to the sequence length. So the sequence length was 3. So these are all the states that we require. Now let's try to fill up the transitions here. Let's try to see what happens when you're in the state S2 and you get the inputs 0 and 1. So you're in the state S2, which is 1 0, and let's say you get the input 0. When you get the input 0, look for a sequence which has the pattern 1 0 0. There's nothing. Look for a state which has the pattern 0 0. There's nothing. Look for a state which has the pattern 0, which is basically the reset state. So when from S2, if you get an input 0, you move to the state S0 and your output is a 0. Now if you get a 1 from S2, now let's see what happens if you get a 1 from state S2. If you get a 1 from state S2, that means that your sequence is detected. So you basically erase this because overlapping sequences are not allowed. And by default, you go to state S0 or your reset state. But now, since your sequence was detected, you are going to assert your output. Now let's complete the remaining transitions. Now from S0, if I get a 0, I stay in S0 with my output 0. From S1, we were done with the 0 transition. Now what if we get a 1? So is there a state with the pattern 1 1? No. Is there a state with the pattern 1? Yes, which is S1. So you're going to remain in S1 and your output is a 0. So this is how you can design a Mealy FSM. Mealy FSMs are typically one clock cycle faster compared to your More FSMs, although their design in hardware is a little bit more complicated.